October 15, 1943. 0347 hours, North Atlantic, 400 miles southwest of Iceland. The pre-dawn darkness hung like a suffocating blanket over the gray swells, broken only by the phosphorescent wake of convoy HX-261 struggling eastward through the hostile waters. Lieutenant Commander Takeshi Yamamoto pressed his eye to the periscope of I-174, watching the silhouettes of 43 merchant vessels crawling across the horizon like wounded whales. What Yamamoto couldn't know was that the small warship he dismissed as an insignificant escort vessel carried detection equipment so sophisticated it had already painted his submarine's exact position on a glowing screen below decks. The U.S.S. Buckley, a destroyer escort that displaced barely 1,400 tons, had just acquired the most advanced underwater detection system ever deployed in combat, and Yamamoto's submarine had become the first victim of America's revolutionary sonar technology that would render the U-boat war obsolete within 18 months. The strategic situation in October 1943 represented the climax of the Battle of the Atlantic, where German U-boats and their Japanese submarine allies had brought Britain to the edge of starvation through a campaign of unprecedented maritime warfare. Admiral Karl Donitz's submarine force had sunk over 3,500 Allied vessels since 1939, creating what Winston Churchill would later describe as the only campaign that truly frightened him during the entire war. Japanese submarines operating in the Pacific and Indian Oceans had added another 184 Allied ships to this toll, creating a global underwater threat that challenged America's ability to supply its allies and maintain its own far-flung military operations. The mathematics of submarine warfare seemed to favor the Axis powers through simple economics of destruction. A single submarine costing $4.2 million could sink merchant vessels worth $50 million or more in a single patrol, while the construction time for a new U-boat averaged 8 months compared to 18 months for a Liberty ship replacement. American naval intelligence had identified the core problem facing convoy protection as the fundamental limitation of existing sonar systems, which could detect submerged submarines only at ranges of 1,500 to 2,000 yards under optimal conditions. This detection envelope gave submarine commanders sufficient time to maneuver for attack positions or escape detection entirely, particularly when operating in wolf packs that could overwhelm escort vessels through coordinated attacks from multiple directions. The Royal Navy's ASDIC system, while revolutionary for its time, suffered from significant limitations in rough seas and could be confused by thermal layers, schools of fish, or underwater topography. German submarine commanders had learned to exploit these weaknesses through tactics developed over 4 years of continuous combat, diving beneath thermal layers, hugging the ocean floor, or using the acoustic, shadows created by convoy vessels themselves. The technical breakthrough that would revolutionize anti-submarine warfare emerged from the collaborative efforts of Bell Telephone Laboratories, Harvard University's Underwater Sound Laboratory, and the Naval Research Laboratory in a crash program that began in early 1942. The development of high-frequency sonar arrays capable of detecting submerged submarines at ranges exceeding 4,000 yards represented a quantum leap in underwater detection technology, combining advances in electronics, acoustics, and signal processing that German and Japanese engineers would not achieve until after the war's end. The new sonar systems, designated QHB by the Navy, incorporated frequency modulation techniques borrowed from radar development, allowing operators to distinguish between submarine contacts and false targets with unprecedented accuracy. The production of these systems required manufacturing precision that only American industry could achieve at scale, with components manufactured to tolerances measured in thousandths of an inch and assembled by technicians trained in 6-month programs that exceeded the entire technical education available to most Axis submarine crews. American destroyer escort crews underwent intensive training programs that lasted 14 weeks, compared to the 6-week courses provided to German destroyer crews and the minimal anti-submarine instruction given to Japanese naval personnel. The training facility at Key West, Florida, processed over 15,000 officers and enlisted men through realistic submarine hunting exercises using captured German U-boats and sophisticated underwater target simulators. These crews learned to operate sonar equipment that weighed 2,800 pounds and required constant maintenance by specialists who understood electronic systems more complex than anything deployed on Axis warships. The psychological preparation of American sonar operators included exposure to recorded submarine sounds, training in acoustic analysis, and practice in maintaining concentration during 12-hour watches that would determine the survival of entire convoys. The mathematics of American sonar superiority became undeniable when examined through production statistics that revealed the true scope of industrial advantage. Western Electric manufactured 2,147 QHB sonar systems between January 1943 and December 1944, equipping every destroyer, escort, destroyer, and cruiser in the Atlantic Fleet with detection capabilities that exceeded anything available to Axis forces. The manufacturing process required 847 specialized components, including vacuum tubes produced exclusively by RCA, precision crystals grown in temperature-controlled facilities, and amplification systems that consumed enough electrical power to illuminate a small town. German attempts to develop comparable sonar systems foundered on the shortage of rare earth elements, the lack of precision manufacturing equipment, and the absence of the theoretical knowledge base that American universities had developed through decades of acoustic research. The operational reality of this technological superiority manifested itself in combat effectiveness statistics that told the story of American industrial supremacy more clearly than any propaganda could convey. Destroyer escorts equipped with QHB sonar achieved submarine detection rates of 89% at ranges exceeding 3,000 yards, compared to 34% detection rates for vessels using older sonar systems. The average time between initial contact and successful depth charge attack dropped from 23 minutes to 7 minutes, reducing the opportunity for submarines to escape or launch counterattacks. American sonar operators could track up to 6 separate underwater contacts simultaneously, allowing single escort vessels to coordinate attacks against entire submarine wolf packs that had previously required multiple warships to engage effectively. The logistical support systems that sustained this technological advantage demonstrated American resource abundance in ways that Axis planners had never comprehended. Each destroyer escort carried 300 depth charges manufactured at the Naval Weapons Station in Yorktown, Virginia, where production lines operated continuously to supply ordnance that German submarines could not replace once expended. The maintenance requirements for QHB sonar systems included replacement vacuum tubes shipped monthly from factories in New Jersey, calibration equipment that required trained technicians available at every major naval base, and spare parts inventories that exceeded the total electronic equipment available to the entire Japanese submarine fleet. American escort vessels could remain on patrol for 45 days without returning to port, compared to German U-boats that required base facilities every 21 days, and Japanese submarines that needed resupply after 18 days of operations. Lieutenant Commander Yamamoto's first indication that he faced unprecedented detection capabilities came at 0351 hours, when the destroyer escort USS Buckley altered course directly toward his submarine's position, despite his periscope being raised for only 47 seconds. Sonarman First Class Robert Mitchell aboard the Buckley had acquired a clear contact at 3,400 yards, a detection range that Yamamoto considered impossible based on his 4 years of submarine warfare experience. Mitchell's training at the Key West facility had prepared him to distinguish between the acoustic signature of a Japanese I-class submarine and the background noise of a convoy traveling at 8 knots, knowledge that Japanese submarine crews had never suspected American sonar operators possessed. The precision of the contact solution allowed the Buckley to close to attack range without the traditional sonar sweeping pattern that had previously warned submarine commanders of approaching danger. Yamamoto's desperate attempt to escape, detection by diving to 200 feet and reducing speed to 2 knots, failed completely as the American sonar system continued tracking his submarine with accuracy that defied everything he understood about underwater acoustics. His war diary, recovered after the submarine's sinking, recorded his disbelief at the American crew's ability to maintain contact despite his evasive maneuvers, writing that the enemy possesses detection methods that make concealment impossible regardless of depth or speed. The psychological impact of this technological superiority became evident in Yamamoto's increasingly frantic orders to his crew, including attempts to use emergency ballast blowing and full reverse power that only served to create more distinctive acoustic signatures for the American sonar operators to track. The technical specifications of the QHB sonar system that sealed Yamamoto's fate represented engineering achievements that German and Japanese scientists would not duplicate until the 1950s. The system generated acoustic pulses at frequencies between 14 and 18 kilohertz, with power levels reaching 2,000 watts, creating detection beams that could penetrate thermal layers and distinguish between submarine hulls and marine life with 94% accuracy. The signal processing equipment incorporated 12 vacuum tube amplification stages, automatic gain control circuits that compensated for varying water conditions, and display systems that presented contact information on cathode ray tubes identical to those used in radar installations. The manufacturing cost of each complete system reached $47,000, equivalent to the annual salary of 35 skilled workers, but American production capacity allowed this expense to be absorbed without impacting other military programs. German attempts to understand American sonar capabilities through captured equipment and prisoner interrogation revealed the technological gap that separated Axis and Allied anti-submarine warfare systems. Kapitän zur See, Wolfgang Lüth, Germany's most successful U-boat commander, wrote in his post-war interrogation that German sonar technology lagged behind American systems by at least 5 years of development, noting that German submarines had no effective countermeasures against the detection ranges achieved by Allied escort vessels. Japanese submarine commanders expressed even greater shock at American capabilities, with Commander Mochitsura Hashimoto of I-58 describing American sonar as supernatural in its ability to locate submarines that should have been undetectable using conventional acoustic methods. The industrial might that produced America's sonar superiority demonstrated the mathematical impossibility of Axis victory through simple comparison of manufacturing capacity and resource allocation. The Anacostia Naval Research Laboratory employed 2,400 scientists and engineers working on underwater detection systems, compared to fewer than 200 German researchers assigned to similar projects and virtually no Japanese personnel dedicated to sonar development. American universities contributed an additional 1,800 graduate students and faculty members to acoustic research programs funded by Navy contracts worth $23 million annually, creating a knowledge base that exceeded the combined scientific resources available to all Axis powers. The raw materials required for sonar production, including 847 tons of copper, 234 tons of aluminum, and 45 tons of rare earth elements, came from American mines and processing facilities that operated at full capacity throughout the war without shortages or rationing. The production statistics that supported American anti-submarine warfare revealed resource abundance that Axis planners had never anticipated when calculating the probable duration of global conflict. Destroyer escort construction reached peak efficiency in 1943, with new vessels entering service every 8.3 days from shipyards in Bath, Maine, Charleston, South Carolina, and Orange, Texas. Each destroyer escort required 1,147 tons of steel, 89 tons of aluminum, and 234 miles of electrical cable, materials that American industry provided without reducing production of other military equipment or civilian goods. The workforce required to maintain this production level included 89,000 shipyard workers, 23,000 electronics technicians, and 45,000 support personnel, representing human resources that Germany and Japan could not match, even by converting their entire civilian populations to military production. The quality control systems that ensured American sonar reliability demonstrated industrial sophistication that Axis manufacturers could not duplicate, despite desperate attempts to reverse engineer captured equipment. Each QHB sonar system underwent 47 separate performance tests during manufacture, including acoustic calibration in specially constructed anechoic chambers, vibration testing that simulated combat conditions, and environmental trials that verified operation in temperatures ranging from 40 to 140 degrees Fahrenheit. The rejection rate for completed systems averaged 3.7%, indicating manufacturing precision that German factories achieved only under laboratory conditions and Japanese facilities never attained during wartime production. American technicians could repair damaged sonar systems using standardized components available at any major naval base, while Axis submarines required return to specialized facilities for equipment maintenance that often took longer than the original manufacturing time. The cascading effects of American sonar superiority transformed submarine warfare from a strategic threat to a tactical nuisance within 18 months of widespread deployment. Submarine sinking rates in the North Atlantic dropped from 96 merchant vessels per month in early 1943 to 12 vessels per month by December 1943, while submarine losses increased from 15% per patrol to 67% per patrol. Over the same period, German submarine commanders began refusing patrol assignments in areas known to contain American destroyer escorts, leading to a breakdown in wolfpack tactics that had previously terrorized Allied convoys. Japanese submarine operations in the Pacific became increasingly restricted to areas beyond the range of American escort vessels, effectively ceding control of the Central Pacific sea lanes that were essential for maintaining communication between Japanese island garrisons. The psychological impact of technological inferiority manifested itself in declining morale among Axis submarine crews who recognized that their traditional advantages in stealth and surprise had been neutralized by American detection capabilities. German submarine crew volunteers dropped from 2,400 per month in early 1943 to 340 per month by the end of the year, forcing the Kriegsmarine to implement conscription for submarine service despite the specialized training requirements. Japanese submarine commanders reported increasing reluctance among crew members to engage American escort vessels, with several documented cases of submarines returning to base with unused torpedoes rather than risk detection by American sonar systems. The propaganda value of submarine warfare, which had sustained civilian morale in both Germany and Japan through reports of merchant shipping destruction, evaporated as submarine successes became increasingly rare and costly. The strategic realignment forced upon Axis naval strategy by American sonar superiority required fundamental changes in resource allocation that weakened other military programs without providing effective alternatives to submarine warfare. German shipyards shifted production from submarines to surface vessels that proved even more vulnerable to Allied air and naval attack, while Japanese naval construction focused on aircraft carriers that lacked sufficient trained pilots and fuel supplies for effective operations. The technological gap revealed by sonar development indicated broader American advantages in electronics, manufacturing precision, and scientific research that Axis leaders had not anticipated when planning for extended global warfare. Post-war analysis by German and Japanese military historians identified American sonar development as the turning point that made Axis naval strategy untenable, forcing defensive postures that played to American strengths in industrial production and technological innovation. The broader implications of this technological superiority extended beyond immediate tactical advantages to demonstrate American capacity for rapid innovation under wartime pressure. The 18-month development cycle that produced operational QHB sonar systems from initial concept to fleet deployment represented organizational efficiency that Axis powers could not match despite their longer preparation for global conflict. American industry's ability to manufacture complex electronic equipment while simultaneously producing aircraft, tanks, ships, and munitions revealed resource depths that made prolonged warfare economically sustainable for the United States while bankrupting its opponents through unsustainable production demands. The verdict of history regarding American sonar superiority in anti-submarine warfare demonstrates the decisive importance of technological innovation supported by industrial capacity and scientific research. Lieutenant Commander Yamamoto's submarine, detected at impossible range and destroyed by depth charges that found their target with mathematical precision, represented the end of an era in naval warfare where stealth and individual skill could overcome technological disadvantage. The 847 Axis submarines lost to American and Allied anti-submarine warfare after the deployment of advanced sonar systems testified to the effectiveness of combining scientific research, industrial production, and tactical innovation in ways that transformed military capabilities within months rather than years. The psychological collapse of submarine warfare as an effective Axis strategy demonstrated that technological superiority, when properly applied and adequately supported, could neutralize entire categories of military threat regardless of the skill and courage of individual combatants. The small destroyer escort that detected Yamamoto's submarine at 3,400 yards carried within its hull the concentrated scientific and industrial might of a nation that had transformed theoretical acoustic research into practical military superiority through methods that Axis powers never understood until after their defeat. American sonar technology represented more than electronic equipment. It embodied a systematic approach to military problem-solving that combined university research, industrial production, and tactical application in ways that made American naval supremacy mathematically inevitable once the full scope of technological advantage became apparent to friend and enemy alike. If you found this deep dive into America's technological dominance fascinating, make sure to like this video and subscribe for more untold stories of how American innovation changed the course of World War II. Share this with anyone who appreciates the incredible engineering achievements that helped win the war.